graphical probabilistic models. We said probability is important in perception because everything is probabilistic. And we need to find somehow model this probability and bring that in account. So we started talking about graphical models. We said we talk about Bayesian methods. We said if we follow Bayes' rule, what was Bayes' rule? Bayes' rule was actually probability of some unknown or hypothesis. We can call it a state, given some measurements or observations, can be modeled based off probability of or likelihood of that measurements given states multiplied by likelihood of that x. This formula is one of the important things that we're going to use it a lot and a lot. And everything related to these things called Bayesian. So if we said, okay, this is a Bayesian method, means divide this, and that called posterior density. So probability of some unknown given some measurements is not equal, is proportion. Proportion means there is some other things here as well, but those things not related to x. You know, if you are saying two functions are proportion of each other, like for example, say, okay, f of x is proportion to g of x, means f of x is actually equal to cg of x, that c is not related to x. C is like a constant or another functions. So this is called proportion. We put this sign like alpha, like this shape. Proportion is important because when you do maximization or optimization in general, we don't care about other parts that are not related to our objection. So we can take them out and make the problem simpler. So anyway, this is the main part of all of the topics that we're going to talk, this formula. And is Bayesian formula. And last class, we started talking about Bayesian net, and we said, okay, measurements model is very generative. So it means measurements like z coming from some like actually states and landsmarking. So it's make a model of parents and child. So Z is like a child, and states like X and L is like a parents, and this relationship can be modeled with the graphical model. That's a and that graph called, we call that Bayesian or BayesNet or Bayesian network. So the Bayesian network actually is a graph. Is a graph, is a directed graph, but we don't have cycle there. Is a cyclic graph, but it's direct graph. So today we're going to talk about how this model is good for measurements, and it's good for like probability of joint probability of x1, x2, and xn. We already explained that we can write that as a product. We can break that down or factorize that with the product of some conditional probability xi given parents of xi. So this was the general idea that said, okay, if we can break down a huge joint probability like that to some factors, and these factors are able to implement with parents and child, so we can make all of it as a graph. The graph makes a visual representation of all of those formula and easier to understand. But this is not still good enough for robotic perception, especially with the SLAM. That is the main part. SLAM, simultaneous localization and mapping, is a more important part and hardest part in robotics. And that's all probabilistic. SLAM is all probabilistic because measurements are probabilistic. I mean, measurements, when I'm talking about sensors, are probabilistic. Environment is probabilistic. Motion plan is, everything's probabilistic. So we need to find a way to model this SLAM in a better way. And we're going to see today that we can do it with factor graph. Instead of using this joint probability, we can go directly to posterior probability, P of x given z. And we can talk about that one. Okay, so that's a topic for today. Let's get started. Before going to details about factor graph, we need to know some more information about probabilistic perception. When we have perception that is probabilistic, we need to know some rules and things. One of them is actually Gaussian prior. Gaussian is actually very important thing in robotics and perception because so many phenomena are Gaussian. Gaussian means this bell shape that we talked about. And this Gaussian model is amazing because it can be summarized just with two values, with mean and covariance. So all of characteristic of this function is this Gaussian function can be summarized with just two numbers, mean and covariance. Also, when you model something with Gaussian, another good point about Gaussian is that you can make a closed form solution. The solution is not approximation, it's closed form because of characteristic of exponential families and this formula, the way that is designed, most of like we don't have approximation and we can find closed form. So in general, Gaussian process has this characteristic. First is closed form. Closed form math, even we call it closed form math, because most of the things can get a proper good form solution, like a function solution, fully described by mean and covariance. Fully described by mu and covariance. What is different between covariance and variance? Any idea? So if you remember, this was variance, and this is covariance. You remember in math, what was the difference? Have you heard about that? Yeah. No? You don't?
I think it's stats, but it was a while ago.
A while ago. Okay, so the what variance means? Varying. How much varying, how much tolerance you have, how much uncertainty you have. And covariance is in a matrix form. That's it. Covariance is when you have a multi-variate Gaussian. When your random variables is not just one, is a vector. Like you have x and y and, for example, theta. If you have x and y and theta as a state. So if the state is a vector, you have covariance. And the covariance is a matrix, is n by n. So this covariance showing the diagonal is still variance. For example, let's make it to the x and y. This theta is going to make trouble because we just have two dimensions. Like sigma squared x and sigma squared y. And this part most of the time is 0 if x and y are not correlated. But if there is correlation, that off diagonal is also showing correlation. So that's a sigma, difference between sigma, and that is the difference between covariance and variance. So anyway, fully described by covariance and mean. Another thing is a smooth and single peak. That's amazing. It's smooth and single peak. So if it's single peak, means maximization and minimization, all easy. And another things, I don't know if I talk about that. We have something like central limit theorem. Central limit theorem. Central limit theorem saying if you are repeating something that might not be Gaussian, if you independently repeat it a million times, the overall is Gaussian. Like, for example, you go to the beach and putting sands on top of each other. Like, but you do it independent. They are independent, and they are like there is no correlation in these things. And the final shape gonna be bell shape. So something like that. Anyway, this central limit theorem helps a lot in so many applications. Like, for example, when you are working with robotics, a noise for so many sensors follow these rules. That's why they consider noise for example, some sensors Gaussian based off this theorem, CLT or central limit theorem, because they are additive noise. They have additive noise. This additive noise can consider Gaussian. Okay. Anyway, and more because I'm gonna talk them later because we need to know some stuff to can talk about those. Anyway, that's why Gaussian is so important. So what is Gaussian? Gaussian saying if, for example, we consider theta as a state, like theta is x and y. If we say theta has Gaussian probability, maybe I just write it here. Yeah, I need to. If we say theta, that is x and y, or even can be a all trajectory. I just consider one, but it can be all the trajectory. With the mean and covariance mu and sigma, it means this part is just for normalization because it needs to be added to 1. The exponential part is important. In this part, what this means, it means if theta is close to mu has higher probability. Remember the shape? If theta is close to mu, it has higher probability. This is probability P of theta, for example. Why? Because when it gets close together, these two become 0. I'm going to talk about this notation here. But we knew that is like distance between theta and mu. If they get closer to 0, exponential family is a maximum in 0. So that's why it's showing kind of probability of the Gaussian characteristic is like that. When you are close to the zero, you have higher probability. It has lots of application, we can see that. But what is this? What is this? We knew before that if we consider this, we call that norm. We talked about this before. This is like distance that we call it Euclidean distance. And this is equal to like theta minus mu transpose in a vector case, theta minus mu. So it's going to be like that. And this is like a distance between 2 points. Like in two-dimensional, theta has x and y, and mu has x prime and y prime. And we can actually find this formula, and this is showing the distance. But what is this sigma here? In this case, we consider there is no uncertainty, or uncertainty between these two are like a circle. Like this is, for example, 1 point, this is another point, or maybe actually like that. Like in this up too. In Euclidean distance, we say distance between this and this is like a circle. Like here is the same distance as this, and this is all same. This is Euclidean distance. So we don't consider uncertainty here. We don't consider, maybe we consider uncertainty, what we don't consider sigma. We don't consider covariance. The covariance sometimes like, for example, covariance if sigma is like 4, 1, 0, 0, this is not circle anymore. This is like this in this case. Because as you can see, sigma x is higher than sigma y. So this is y, this is x. So in this case, in reality, this point and this point, they might have different size. If you consider Euclidean distance, these two have different size. But if we consider sigma, they have same size. This distance called Mahal distance. I'm going to clean this up. Mahal distance. So that's very important in robotics because we need to consider uncertainty. And distance is one of the important part. We want to find distance to the wall. You want to distance to the target. And the target is moving. So when the target is moving, this sigma in x and y is different. So we need to find this distance properly. And we can't use Euclidean distance anymore. We need to use Mahal distance. We need to kind of use, okay, let me clean this up, use this uncertainty properly. That's called Mahalanobis distance, or in summary, Mahal distance is the name of that. And the Mahal distance is actually considering sigma in this between. In Euclidean distance, the distance was just multiplying these two matrices, transpose and itself, without this sigma between. But this sigma, or inverse of that sigma, makes it like a normalize that. And this is very important. This kind of distance called Mahal distance. And what else I can say about Mahal distance is very important in robotics. It's very important in robotics. Mahal distance is the way to measure how far a point is from a distribution. That's a very good explanation. It's showing how far you are from a distribution. It's not just a point. It's not just a mean. It's a distribution. So normally, mean is a point, but distribution showing the covariance or variance around the mean. And we want to find that distance of, for example, x to, this is, for example, L, wall, for example. You want to find this distance. And, or here, let's consider it mu, for example. So this distance, we need to consider covariance. Okay, that's called Mahal distance. That is very important. Have you heard Mahal distance before? Or normalized distance. Sometimes they call it normalized distance. When you are dealing with uncertainty, or when you are dealing with probabilistic perception, that's something that you need to know. We always use another things that in robotic or tracking we are using, we call it gating. We want to, for example, assign, for example, we have a target that is moving and we are tracking that. And this is like a noise around the measurements. And we want to see which measurements are actually can assign to the target, which one is outliers. So we always consider a gate around the target. And that gate is also coming from Mahal distance. That gate specifies which measurements is can be associated to the target, which one is like outliers. So that's also another application of Mahal distance. So Mahal distance has lots of application in robotics. It's good to know that. Okay. So let's clean this up. Priors on the robot positions, landmarks, or initial state often use Gaussian distribution or densities. So Gaussian distribution are very important for us. And another good point about Gaussian, if some other things are not Gaussian, we can approximate them as a Gaussian. That's good point about Gaussian. We can see more about Gaussian. Another thing is about measurements model. That was kind of prior, this one. This was prior. Why this was prior? Why this look like prior? Prior was some assumption that we are doing. Why this look like assumption? Are we assuming something?
We're assuming it's in the distribution.
Gaussian. Yeah, we are assuming that distribution of unknown x is Gaussian. This assumption makes all of our prediction like a little. We are doing based off that assumption or prediction. So the prediction, if we find, for example, theta at the end or theta star, this theta star, even though you are finding the exact, closed form solution, and still that closed form solution is not optimal. Why is not optimal? Because we assumed that this is Gaussian. That's why it is called approximately optimal. This is, when we put a star here, it means it's optimal. But when we do this assumption, it makes it approximately optimal. Approximately optimal. This was very important for me. I was, when I started working in these topics, I submitted papers and I always get lots of, reviewers always give lots of comment. And they ask me, okay, how this can be optimal? And I try to explain, yes, this is optimal because of you're getting closed form solution. How this not be optimal? And then I realized that it is not optimal because of that assumption. We need to say this is approximately optimal. So that's something important. So yes, so that's the assumption. But we are assuming for x, so this is prior because we are assuming x or theta. I mean, theta is actually a state. the state, this is kind of prior information about the X. But this prior, if we go for measurements, that's gonna make likelihood. That's gonna make likelihood. We also can assume measurements are Gaussian in the case that measurements are Gaussian, because measurements generative formula is like that. You have a h of x and L, and you have sigma. That sigma is considered Gaussian, and h is measurements prediction. So I think last class I explained what is h. H is kind of transforming from a space to measurements space. We're going to see another example here, like, and if this is, if z is Gaussian, we can write it like that. We can say probability of z given x and L, that is actually likelihood of z given this is a normal distribution around this prediction with a noise or with a covariance that is measurement noise or measurement covariance noise. This R is a symbol for measurement noise. And this H is showing that's the prediction, and that R showing this uncertainty around that. So example, like for example, if you are using, clean this, if you are using, for example, bearing measurements where you are measuring angles, like for example, you have a landmark here. That's your landmark, landmark X and landmark Y, and you have X, that X has XX and XY, okay? So if you want to measure the angle between this angle, alpha, for example, is coming from this formula, arctangent. So because alpha is arctangent of this, that is actually Lx minus xx over y minus xy. So as you can see, this is not linear. Arctangent is not linear. If we put arctangent 2, we are dividing these two together. When this becomes 0, this can handle it, you know. But when you divide it here and use, just because there is two functions, arctang and arctang2, that's a difference. I think we talked about that before. So this is in this example, I want to tell you first of all how we can transfer between these two spaces. A space of measurements is angle. A space of states is Cartesian space, x and y. So we are moving in this space with this nonlinear function, but it still is Gaussian. The model still is Gaussian, even though the H is not Gaussian. Why is Gaussian? Because you can write it like that. This is very, very interesting. So probability of Z given X and L, that is likelihood. This is likelihood. This likelihood is Gaussian. This part is for normalization. And this is exponential family, and that's the exponent part. Exponent part is an important part, because that's the only part that stay in optimization. When we optimize this one, they're all gonna get out, because that part is not related to x, gonna get removed, and this exponential gonna get out too, because we can get log. because if we say x, let's call it theta, that's a very important part. When we say theta star is max or mean of f of these, we can also say same thing with the log of that. Max of log of f of. Log is not changing the trend of the function. That's very important. So always you can put a log there without any problem. And if you put log here, the exponent and log gonna cancel out each other. And just exponent's gonna stay out. This exponent is important. And this exponent look very familiar, no? It look like least square. And we can see how amazing. That's another characteristic of Gaussian assumption. Okay, so we already saw how prior model and measurements model can be Gaussian, especially in robotic case. Let's go about motion model. We can talk about motion model more. So motion model normally explain how we are moving from x in time t to x time plus 1. Or sometimes in discrete format, we call it k, xk and xk plus 1. So this is motion model. So motion model is probability of xk plus 1 given xk or xt. If xt plus 1 is just related to one step before, this kind of process called Markov process. Markov process. Because it just depends on the one step before. It's not depend on very past. However, for Markov model, we have different degrees, like for example, 2 degree of freedom Markov model, 3 degree of freedom Markov model. Like most of the time it's 2 degrees because it's not just x, also velocity. If we put acceleration, it's going to be 3 degrees. But generally, we don't need to worry about that degrees. When we are talking about Markov model, means xt plus 1 is just related to xt. However, xt plus 1 might be x, y, x dot, and y dot. Okay? And that's called Markov model or Markov process or Markov chain. Actually, if it's discrete, it's Markov chain. Markov process is a continuous version of that. Anyway, this is a motion model. So the motion model specifies what is the relationship between states in different time. And is important, and most of the time this relationship is not linear. The relationship between xt plus 1 and xt is most of the time is not linear, especially when you have some angular velocity. If you have some angular velocity in I think we talk about that when you have angular velocity, when the robot has some steering wheel, that direction is important here. So imagine the robot is like that. And this angle is important, like we call it omega. And xt plus 1 is equal to xt plus v cos of theta delta t. And yt plus 1 is also yt plus velocity cos of theta delta t. And this is theta. And the theta also is another part of a state in this case. Theta t plus 1 is theta t plus omega delta t. That omega can come from IMU sensor. So in this case, and most of the robots are like that. Most of the robots, they have actually this angle. If they are in this format, it's called wheeled robot, or sometimes unicycle robot. Also unicycle model, we call it unicycle, or sometimes just constant velocity, but velocity in this case consider angular velocity and normal velocity. Okay, so as you can see, this is the model that I'm talking about. This is the motion model that I'm talking about. And where this model coming in a Gaussian, that I clean this up here. That relationship between xt and t plus 1 is going to this formula, g of xt and u of t. These stuff are very important, but maybe you don't see them now. Later when we use them. When we use them, for example, for multiple robots that they need to follow each other or make formation, or they need to do something together, we can see how amazing this formula can add together to make a kind of great project or optimization problem. Okay, here g of t, g of xt and u of t is considered motion function. Motion function was that formula that already wrote about robot. And this u of t is just the input. This just can be noise. So yeah, and q is also uncertainty, but this uncertainty is for motion uncertainty or covariance, and motion uncertainty. Similar to measurement, so most of the time for measurement uncertainty we consider R, and for a state uncertainty, because here is a state, X is a state, we consider Q. But same thing. Both of them consider Gaussian most of the time. Okay, motion model are often nonlinear, but even though the motion model are not linear, we consider motion model Gaussian. So it can be nonlinear but Gaussian, that's fine. It's not linear because you are not moving in a straight line. Okay, so maybe I put this for the next class. I want to just a little explain why BaseNet is not enough for us to actually do probabilistic perception. Probabilistic perception is whatever we started. We want to see robots are not very precise sometimes, and they have probabilistic things that happening. So we need to model that. BaseNet was good for measurements case because measurements is kind of father, parents and child relationship, but the things that happening in robotics and probabilistic perception, most of the time we don't care. We don't consider actually measurements as a state. In BaseNet, we consider measurements as a state. If you remember in the diagram, we consider, okay, this is landmarking, this is measurements, and this is, for example, X. So this is a state, because that's a graph. Is not this graph. All nodes are states, and this actually relationship between these states considered with a directed graph. So this is not very is not enough for us. We need something to show. We need to and BaseNet showing joint probability P of X and L, for example, and Z, something like that. This is not very important for us. The one that is important for us is inference. We need something like P of X given Z, or X and L given Z, if we consider landmarking as well. So we want something like that. Also in BaseNet, we were mentioning that this is a product of P of, imagine we all consider all of them X, X1, X2, and so forth. Probability of Xi given parents of X. So this is very weird and sometimes gets so complex. But what about, instead of these, we consider another things like factors. We consider product of factors. Factors are a function of X. Let's just consider this all together, 1X. Function of X. And this factor is kind of relationship or probability, like an express of probability. The factor is express probability for a state Xi. Like, for example, can be motion model, can be a sensor, can be just a local constraint, can be everything. And make this graph much easier, and also is not directed anymore, is undirected. But the only thing is in factor graph is that factor graph is bipartite, means you have two kind of nodes. Some nodes are states, some nodes are the black one, can be different shapes, are factors. I'm just going to show you one of factor graph that I was working on for the last paper that I was working. No, not this one. I'm going to talk about that last class too, but I just want to see how amazing is that. This is 3 robots that are supposed to make a formation. And this is a factor graph that summarizes everything. We have some prior information about the position of them at the beginning, and some, for example, this circle is obstacle avoidance, and this actually diamond one is a formation factor. That's showing how they are making formation, and I will run this code for you next class. And you can see this is like simulation. The 3 robots at the beginning, they are far from each other, and then make a triangle, and they move in a triangle shape to go to destination. This is all possible with just these ideas that I explained. It's just like a basic